back, and then you reply to that. The one it sends back will have the opposite size initial sequence number. You then have to send that back in order for the TCP connection to succeed. If you spoof your source address, you'll never get that packet, and the connection will be pulled down. But if you can guess what it's going to be, because it's not a random number, then you can keep on carrying on this communication. You can spoof a source address. Perhaps you can spoof the source address as an IP address inside this network. And up till quite recently, a lot of services used IP-based authentication, for example, R-shell. And this will allow you to run arbitrary commands on hosts you shouldn't. This isn't much of a problem now. Most hosts, or most desktop operating systems now know how to produce non-random, non-predictable IP TCP initial sequence numbers. There are some problems with embedded hardware. The reason it might be useful for steganography is, firstly, it's big. It's 32 bits compared to the IP ID, which is only 16. And if it's unpredictable to everyone not involved, then it's also unpredictable to the warden. Remember, he knows the operating system, but he doesn't actually have access to the computer. And there's been a variety of proposals for using this, but doing it is a lot harder than you might expect. I'm going to talk about some schemes that have been proposed and how they slip up, and then I'm going to propose how this can be fixed. The first one is NUSHU. This is proposed at the last Scale Communication Congress, and this is what got me interested in this subject. It's been implemented for Linux. It's a very clever scheme. It has reliability. So when you send out a packet, firstly, there's reliability information embedded in it. Like a small version of TCP, it has a packet number, and that means if packets are lost or reordered, you can reassemble it. And then it's encrypted. And then there are tricks in the Linux kernel which hide it from someone who's on localhost trying to inspect it. What I'm going to look at is not the localhost detection, but ones on the network. The reason encryption is used is to make the initial sequence numbers look random, and on a first glance, they are unpredictable. You would think that because they're unpredictable, that they're going to be random, but in fact they're not. So here's a graph comparing Linux and NUSHU. The first thing you'll notice, I'll explain what the axes are. On the x-axis is a particular initial sequence number. On the y-axis is the following initial sequence number. The first thing to notice about Linux is the scale. It doesn't use anywhere near the whole space of initial sequence numbers. It only goes up, everything starts with 9, but it's fairly evenly distributed above that. The red dot in both axes is the mean for that axis. The other thing to notice is there are not large changes. So there's nothing in the top left-hand corner and the bottom right-hand corner, and those are the ones that signify changes. If you compare it to NUSHU, here it's very evenly distributed, and it uses almost the whole space. So it's probably possible to detect NUSHU just from doing this analysis, but it should be possible to do better. This is how NUSHU encrypts packets, initial sequence numbers. The requirements from this are the initial sequence number output should look random, and it should be possible to decrypt every packet by itself. This is because packets might be lost and you don't want to rely on everything being received correctly before you can decrypt anything. The other problem is most block ciphers, like DES, which is being used here, are 64-bit up. AES is a 128-bit block. And that means it can only encrypt that size or some multiple thereof. So instead of using it in normal mode, it first takes the source port and destination port, the source address and destination address, and XORs these together. It appends NU to pad it up to the appropriate length, and then it encrypts this using the secret key that's shared by Alice and Bob, and this gives you another 64-bit output. Because you only want 32 bits, that's how large an ISN is, you XOR your message along with all the reliability information with that, and you get the new initial sequence number. Problem with this is there's going to be frequent duplications of the highlighted fields. The source IP address is not going to change for most hosts. It's pretty much fixed. The source address there's not going to be much variation in those. Destination port, if you're doing a lot of web browsing, that will always be 80. The worst case is if you're using a web proxy, then the destination address is always going to be the same. The port is always going to be 8080. The source address is always going to be the same, and you've only got the port number, the source port number left. At best, that's going to be 16 bits. In practice, it's going to be a lot less. When I've been looking at some packet dumps, in practice, about half of the packets you receive are going to be duplicated in this way. In order to understand why this is a weakness, I'll give you a very brief background of XOR. If you take a number and then XOR it with itself, you get 0. And all that means if you take a message, you encrypt it with a key, you take another message and encrypt it with the same key, and then XOR those two, then the result will be the two messages XORed with each other. And if both of these messages are the same, the result is going to be 0. But even if they're not, you can still pick up patterns. For example, assume the message is all ASCII. In ASCII bytes, the top bit is always 0. That means when you XOR two ASCII bytes, the top bit of that is always going to be 0. And there are similar patterns for anything else you can find. And this is the result. This is slightly different from the previous graph. The x-axis is still the current initial sequence number, but the y-axis is the next packet with the same initialization vector. That's the same source port, destination port, source IP address, and destination IP address. And on Linux, this is more or less random, apart from the limited scheme, the limited range. But I think it's clear that Nushu is easily detectable. This is because all packets were sent with the empty byte. So that meant that they weren't all 0, but they were all the same. And that's what this graph shows. It's possible to avoid this, for example, by eliminating the repeated IV problem. You could hash more of the header, and that will give you a bit more randomness. You could use a different style of block cipher. But that will only work if initial sequence numbers are random. But if you look at how Linux generates them, it's not quite the same. The requirement for initial sequence number should be unguessable by people not involved in this conversation. And the conversation is defined by the source, destination, port, and IP address. So what Linux does is put these 3 bytes into 32 bits, and then I'll also add a random number to bring it up to 4 bytes. Then it takes a reduced version of MD4. This is a hash function. You feed it a variable length input, and it will give you something which depends on that, but shouldn't be possible to map back. And it also throws in 256 random bits. This is only known by that host. And then you take the second byte, from that, because you, and then, the second 32 bits. Then you replace the first byte with a counter, and then add on the time. The reason you have a counter is MD4 is known to be weak, so acting conservatively, the key, the 256 random bits, is changed every 5 minutes. But once you change that key, it's possible that you're going to get something very similar to the last initial sequence number, and then you might risk a collision. So replacing the counter at the beginning, which is incremented on each rekey, should hopefully prevent that. And then the reason you add the time is it's possible a TCP connection will be recycled. If it's cancelled and then retried, you don't want to use the same initial sequence number in case the packets are still on the internet. You want to be able to differentiate the dead connection from the live one. And so you add the time in microseconds. This is going to lead to some patterns. If you have the same rekey period, in the same rekey period, you're going to have the same key. And if you have the same initialization vector, that is source, destination, port, and IP address, then the input of MD4 is going to be the same. The key is the same, so the output is going to be the same as well. That means that all you have left is this timer, and the difference between two initial sequence numbers is going to be the time in microseconds. That means that even if you fix the problems that Nushu had, adding a bit more randomness, and if you ever see you're going to send the same data with the same initialization vector, you do something different, then you'll never have the collisions that I showed before, but it will look random, but Linux doesn't look random. So on the left-hand side is what Linux would look like, or Linux does look like. I've tried to send packets out as fast as possible, all with the same source port, source IP address, and destination IP address. And they're all more or less clustered on the left-hand side of the graph because the Linux was able to send about one packet every 2 milliseconds. But on the y-axis, I've stored the difference in initial sequence numbers. And you can see in Linux, there's very good correlation. And in fact, if you look at, say, the packets at 3 milliseconds, that corresponds to a difference of about 3,000. That's because that's because the difference is due to that 1 megahertz counter, which corresponds to microseconds. If, on the other hand, you randomize the initial sequence number like a good cryptographic function would do, then you still have the clustering on the x-axis because that's when the packets were sent, but they're very evenly distributed on the y-axis, and this would be trivially spottable. In order to do good steganography for Linux, you have to emulate as closely as possible the way real initial sequence numbers are generated. The difference is you want to be able to get the information back out, whereas Linux is designed for the exact opposite. The way I propose to do this is you take the lower 3 bytes of the initial sequence number and replace that with your data. If you remember, comes from MD4, so is hopefully unpredictable. You can't do anything about the top byte. That's where the rekey counter has to be, so you put that there. Then you also have to worry about what will happen when the time was added on. This might cause a carry into the rekey counter, which the attacker would be able to see. So you compare the current time in microseconds with the data you added, and if the result is negative, then you add one to the rekey counter, and that should hopefully patch all that up. Then you also have to correct the checksum, and also the IP ID. I mentioned that this is a counter. In the case of TCP, the initial value comes from the TCP initial sequence number. There's no reason for this, but it's as good as anything else. But if you assume that the initial sequence number is random and the attacker is aware of how Linux does this, then you can be caught out. You have to worry about packets being lost. IP packets get lost all the time. But in the case of a TCP connection setup, if the connection succeeds, you'll see an ACK back. If not, then you can assume that packet was lost. But you still have to make sure that what is coming out of MD4 really is random. So you have to achieve freshness using a good initialization value. Instead of just XORing the source destination port IP address, you put that into a hash function, and that dramatically reduces the number of collisions. That should only be about 1 out of 50,000. And whenever you see that you are going to have a collision, then you make